Today I will talk about the concept of work and energy in physics. The word work may have some different meanings in daily life. For example, if you do some work, we generally get tired. Maybe we get bored by doing some processes, by applying some forces. Maybe at the end we get tired. For example, if I hold this armchair in this position for hours, maybe for 2 hours, I get tired, sure. However, physically, I do just a very little amount of work. It is just in the lifting up part from the ground to this position. And if I wait in this position for 2 hours, physically I do no work at all after lifting it up. So let's define the work in physics. Work is a dot product, scalar product. Remember, we have seen the concept of scalar product. For example, the scalar product of two vectors. First, let me write we have seen u dot v. U dot v was a scalar product. It is defined in two ways. Ux, Vx plus Uy, Vy, Uz, Vz on the one hand, and magnitudes of u and v multiplied by the cosine of the angle theta in between. This was just the definition in chapter 1 when we saw the vectors. Now we will make use of this dot product in the definition of work. W, capital W is generally used for work, is a dot product of two vectors. One is the force applied, the other is the displacement. Of course, this doesn't have to be in the x-axis only. It can be in y direction or any r direction, but in general it can be written as a dot product, as a scalar or dot, remember, product of these two vectors. Since the result work is a number, we don't have a vector sign on top of it. So when you multiply f and x, but it's not just f times x. What is the definition? It is the now we neglect the we do not draw these vectors arrows on top. F times x times cosine theta, using this definition. In some cases, we will also make use of the first one. Now, what do we mean by this expression? Of course, we will give physical examples to this. For in the simplest possible case, we have a block on a surface, on a horizontal surface, and assume there is no friction. And we try to pull it to one side by a force F. For example, we manage to move the object to a new position. That new distance is, let's say, from the beginning, is x. In this case, W equals F times x times cosine theta. What is angle theta? Since F is a vector to the right, x is a vector to the right, there is no angle between them. They are parallel vectors. So cosine 0 is 1. So we have cosine 0, which is 1. Then in the simplest case, we have W equals F times x. Maybe we have learned it previously as just force times distance, but this is just only for the simplest case, where force and displacement are parallel vectors and there is no friction between them. However, if we have an angle between these two vectors, for instance, if W, if the force we apply, for instance, makes an angle theta, then W will be, and of course we bring the object to the final position of distance x from the first, then it is F times x times cosine theta. And we understand immediately that if theta equals 90 degrees, for instance, if f and x are perpendicular vectors, then there is no work. In which cases a position. For example, when we bring the object to a new position x from the beginning, but during this motion, of course, this is the object, free body diagram, mass m, and there are three forces acting on it. One is the weight, mg. The other is the normal force, n, applied by the surface. And also, we exert the force F on it so that it is moving to the right. And assume there is no friction yet in this motion. Work done by our force is, yes, F times x. Because F and x are, as we said here, they are parallel vectors and there is no angle. But on the other hand, Wg, work done by gravity, which is work done by the weight of this object, is just weight mg times the distance but cosine 90. Similarly, work done by the normal force. It is the force acting up, but x is this displacement along the x-axis. So that normal force times the displacement times again cosine 90. So in these two cases, both Wg and Wn, in other words, work done by the gravity, work done by the normal force are both zero. So there are cases where, although we apply a force, there is no work done. First of all, there should be a displacement from one position to another. We should apply a force, or there should be a force acting on it, and also there should be an angle between them other than 90 degrees, because cosine 90 is zero. Now let me compare a few cases based on this. For instance, also, this is a case where, for instance, if you apply a force making such an angle and bring it to a new position, x is the displacement from the beginning and this angle theta, again, W equals f times x times cosine theta. Now let's see some other cases where we have some inclined planes. For instance, if we have an inclined plane like this at an angle theta, and we bring an object, a block of mass m, by applying a force F to a new position. For instance, this is the height y. What is the work done by this force F? What was the definition? Wf was force F times displacement, but displacement is not y, it is just this displacement. Let me call it, for instance, r. F times r times cosine of which angle? It is not this angle theta, of course. This angle, whose cosine we have to multiply, is the angle between the force and the displacement. In this case, F and R are parallel vectors. There is no angle, so this is cosine 0. And cosine 0, we know, is 1. So this is F times R. But R is not given by the problem. It is Y which is given. And from this triangle, we can express R in terms of height Y. So this is height y, that is r, which is unknown. This angle is theta. So y is equal to, very simply, r times sine theta. So r can be written as y over sine theta. So in this case, work done by our force is just F times r. What is r? Fy over sine theta. So to write it as Fr cos 0 or F times r is not the proper result, because r is a quantity which is not given by the problem, so we should be able to write it express it in terms of given parameters. Given parameters are, for instance, height y and angle theta. So y, or this is the result for the force exerted, for the work exerted by, done by the capital F. But during this motion, also the gravity does some work. Let's find it. Work done by gravity. What is it? Let's apply the definition again. Force mg times this displacement r times the angle, cosine of which angle? What is the angle in this case? Let's write it. This is one vector r, the other vector is mg, and this angle is, let's call it phi. We should write phi here. But phi is 90 plus theta. So phi is, the angle between them is 90 plus theta. And cosine of an angle 90 plus theta is just negative of sine theta. So if you have an additional part after 90, then you should write sine of that angle with a minus sign, according to a trigonometric relationship. So this minus sine theta should be substituted here for cosine phi. Therefore, work done by gravity is mg r with a minus sign and sine theta. But we also have seen here r sine theta corresponds to the height in this lifting up process, height y. So this part, r sine theta, corresponds to the height covered, this vertical distance upward, so that it is work done by g is minus m times g times y. Of course, you may remember minus mgy or just mgy as a potential energy. We will see soon what the potential energy is. But right now we don't know it, and we only say we talk about the works done by different forces. So this is the work done by gravity during this transportation from initial position 1 to the final position 2. Now we can also introduce now the friction that we have learned last time, friction force. Work done by friction force F, if there is any, is, okay, assume that there is now some friction between the block and this surface, some coefficient mu is given. In this case, in addition to the work done by our force and the work done by gravity, we will also have some work done by the friction force between the block and the inclined plane. Again, let's write the definition. We know that little f is used for friction forces. It is that force times displacement and the angle between them. Cosine, let me call it beta. Cosine beta. What is beta? Beta in this case, let's first find it. This is the object, block, and that friction force acts down, but displacement r is this way. So this angle, beta, is in this case 180 degrees. So we have to write here cosine 180. Well, what is cosine 180? It is just minus 1. So that work done by friction will be friction force F, displacement R, and with a minus sign. But we don't know F and R yet. The problem doesn't give us F directly, it doesn't give us R directly. So let's write these two quantities in terms of given parameters. Along this plane, let's see the forces. In the free body diagram, we know that this is the weight mg, that is the normal force, and of course mg has two components. One is perpendicular to the surface, the other is parallel to the surface. This is like a rectangle, and we know that this is mg cosine theta, that is mg sine theta. But also there is a friction force acting down the plane because we want to pull it to a higher position along the plane. And also we know that these are equal and opposite. So n is mg cosine theta. But f takes its maximum value, we are sure about it, f takes its maximum max, but it is mu times normal force. It is mu times mg cosine theta. And this angle, because r is a vector along the plane, so between f and r, the angle is 180 degrees. So that work done by friction, we continue from here. With a negative sign, F, what is the friction? It is mu times mg cosine theta. And then r, what is r? R we have seen y over sine theta. So work done by friction in this case is a negative work, of course, because although the object is moving in this direction up the plane, friction is acting down the plane. So the angle between them is 180 degrees, pi radians, as we will see later. And cosine 180 is just -1. So that we can write it as mu mg y and cotangent theta, or just write it as cosine theta over sine theta. So this is the work done by the friction force. Now let us define a new quantity, kinetic energy. We will come to the concept of potential energy later. What about kinetic energy? Now I assume that we have a horizontal plane and a block of mass m moving with some initial velocity v1. And there's no friction also, for example. And I assume that we apply, and we pull it by some force F during this motion. And this is the first position, initial position, and later on, after a time, it covers a certain distance x, and it is passing by the second position with a new velocity v2. And this displacement is, let's say, x between 1 and 2. So if you don't know what the concept of kinetic energy, work, etc. are, then we can apply the one of the previous equations. Remember that v2 squared, final velocity, when it passes by the second position squared, is just initial velocity squared plus or minus, but let's take it plus now, 2a times x. X is the distance between the two positions. Okay? This is one of the kinetical equations that we have already learned. So fine. One of them may be 0. For instance, if it stops at the end, v2 may be 0. If it starts from rest, v1 may be 0. Otherwise, they are both non-zero numbers. Let's have three. We can have three possibilities. One, for instance, if v1 is greater than v2, we have a negative acceleration. It slows down, maybe it stops. If v1 is equal to v2, there is no acceleration. If V1 is less than V2 and acceleration is positive. Okay. Now let's multiply these terms by mass m of the object. By multiplying through by mass m, what do we get? We have m times v2 squared equals m times v1 squared plus m times 2ax. Now dividing by 2, dividing through by 2, we have mv2 squared over 2 mv1 squared over 2 and m2ax over 2. So these 2's will cancel. What do we get? Let's take this term to the other side. Let us define 1/2 mass times velocity squared, this term, this product, as a single term. It is the kinetic energy of the object. Kinetic, this is, let's say, kinetic energy of the object. So it depends on the mass of the object. The greater the mass, the heavier the object, the greater will be the kinetic energy, obviously. Also, it depends on the velocity. It depends on the velocity further because it is dependent on the velocity by squared. If you double the velocity, kinetic energy is increasing to 4 times. If you triple the velocity, kinetic energy increases to 9 times the first. So it is very strongly dependent on the velocity of the rather than the mass. So this is the definition. But as you see, there are different indices, V1 and V2. So this corresponds to the kinetic energy of the object in position 1. This corresponds to the kinetic energy at position 2. Then what about the other additional term? So we can take it to the other side. 1/2 and let's write them separately. V2 squared minus 1/2 m V1 squared is equal to mass times acceleration times distance. But what is mass times acceleration? It is, according to Newton's second law, this part is just the force applied. And we know that for a case where f and x are parallel vectors, there is no angle, cosine 0 is 1. So this is just the, it's just equal to the work done by the force. Maybe negatively, maybe positively. Okay? And this part, let's define it as K2, kinetic energy K, capital K, because little k is used for the force constant of the spring. Please don't confuse the letters, especially in physics. Notation is important. Notation is how you write your variables, constants, etc. Capital K for the kinetic energy. If you have a little k, lowercase letter k, it is for the force constant of the spring. So capital K2 for the kinetic energy at position 2, kinetic energy at position 1, and we have a subtraction. Whenever we have a subtraction of a quantity, we have, remember, change delta. Delta K is just work done by the force F. So this is the basically work energy theorem. Work energy theorem. What is the unit of work or energy? So work and energy are corresponding quantities. They are similar. They have the same dimensions. They have the same units. So energy, work, W, and energy E have the unit of joule. Capital J is the abbreviation. Unit of joule in SI. What is SI? It is Système International. It is the system of units accepted for physical processes in general. If force is in newtons and displacement is in meters, then energy or work in joules. The other possibilities are in the CGS system, for instance, centimeter gram second. Force is defined in terms of dynes. Let me also write, although we don't use them frequently, let me just talk about briefly. If F is in dynes, X is in centimeters, not meters but centimeters, in that case, energy or work is in X. Okay? So this is another choice. But in this book and in our course, if some numbers are given, they are given in SI. And in SI, in the system we use, forces are generally expressed in terms of newtons if numbers are given, otherwise it's just F. Displacements in terms of meters, and therefore energy or work, both are written, expressed in joules. And J, capital J is the abbreviation. Please don't confuse capital J for the unit joule with the unit vector J, little j, with a cap for it. Don't confuse them, please. Or little k and capital K are different things. Let's have an example on this work energy principle, for instance. A car of mass m is initially moving at velocity v0 and is entering a region where the coefficient of friction is mu. So let me draw a simple picture for this. Here we have a car, although not a good one. Well, this is a car. It is moving at the initial speed of v0, so we are stuck to use the given parameters v0. It is not v1, it is v0, for instance. At position x equals 0. And assume that this is a rugged surface, so there is a coefficient of friction mu between the tires and the road. And here it slows down, obviously. We assume that the driver doesn't give additional energy to the car, so that it slows down. Maybe here, somewhere there, it will stop. So we can ask different properties. So capital M is the mass. Part A. At which value of x does it come to rest? B. At which value of x does the velocity drop to 1/2? Of course, 1/2 of initial value. part C can be added to this. It is just the opposite way. If it covers a distance L, if it covers a distance L before stopping, what will be its velocity at x equals half of it, L over 2. So these are the three simple questions in this problem. Of course, we will apply work energy principle. What was the work energy principle? Work done corresponds to delta K. But work done is the work done by friction in this case. It's a negative work. Work is, in this case, work done by friction. And work done by friction is a negative quantity because as the object is going to the right, because x is a displacement in the positive x-axis, friction force is acting in the negative x-axis, so that the angle between them is 180 degrees, and therefore cosine 180 is just a -1. So that work done by friction, let's first find it. It is friction force and displacement. Assume that it is a displacement x until it stops. But it is friction force times distance. Let me write it as L, because it says L is the total length it can cover, F times L, but with a -1. Cosine, coming from cosine 180. So it is minus F times L. What is F? F is coefficient of friction times normal force. But what is the normal force? If you consider this free body diagram, weight mg is acting down, normal force is acting up, so that, and they are equal and opposite, so it is mu times mg. Now work done by friction is negative mu mg for the friction part, L is the distance. And this quantity is just equal to change in the kinetic energy. But delta K is just, let's say, K initial minus K final. K initial was 1/2 capital M. Initial velocity was given as V0 squared, minus the final value, which is 0 because it stops. We want to find the distance L until it stops. If it stops at the end, there is no final kinetic energy, because kinetic, the word kinetic comes from kinematics, cinema, motion. If an object has a velocity, it is moving. It means it is a kinetic quantity. Cinema is the sequence of pictures. There is a motion. Motion, velocity, kinematics, cinema, they are all in the same context. So that if there is no motion, if it stops at the end, there is no kinetic energy. Therefore we have minus mu mgl is the work done. It is minus 1/2 capital M V0 squared. So capital M, sorry, let's not change the letter. This is capital M because it is given as capital M. Alright, this is also capital M. So these capital M's will cancel, minus sign will also cancel, so that we want to find L, and L is equal to V0 squared over 2 was already here. Mu times L, mu and G come to the denominator. So L is equal to V0 squared over 2 mu G. Of course, as you see here, mu comes in the denominator. It means the greater the comment, then we write a an immediate comment, mu appears in the denominator as expected. For instance, this coefficient cannot be in the numerator, it should be in the denominator, because the greater the coefficient, the harder the friction. So that distance covered should be less and less. As the coefficient of friction gets larger, it will be more difficult for the car to go further and further. So L should be less and less. If mu were here, it is an obvious mistake. Mu appears in the denominator as expected. The greater the coefficient, the greater the friction, the less will L be. L is the total distance covered. Let's immediately find part B. Part B is at which value of x does the velocity drop to 1/2? It is easy to get it using the same expression. Part B, velocity drops to 1/2. So we want to find 1/2 m v0 over 2 squared minus 1/2 m v0 squared. It is just equal to mu times m g and x. Now we want to find this x. It is not L, of course, it is something less than L. And it is easy to cancel the masses, first of all. This is a negative quantity, this is also a negative minus the work done. So we have here, let me continue here, 1/2 times v0 squared over 2 minus v0 squared is minus mu g and x. Now this is, v0 squared over 4, sorry. When you take this, it is v0 squared over 4. So 1/2 times v0 squared times minus 3 over 4. 1/4 minus 1 is minus 3 over 4. It is equal to minus mu times g times x. So x is easily found. X becomes, these minus signs will cancel, 3 over 8. 3 over 8, v0 squared over mu and g. Okay? Remember that this is 1 over 2. It is 4 over 8, in other words 4 over 8. This is 3 over 8. 3/4 of the total distance. It reaches the half velocity at 3/4 of the total distance covered. Let me finally get the final part. If it covers the distance L, before stopping, what is the velocity at L over 2? 1/2 m v0 squared minus 1/2 m v. Whatever this v is just minus mu mg L over 2. Again, cancel the masses. So mass doesn't enter in these calculations. And also let's cancel all the 2's. We have v0 squared minus v squared. It will be minus mu g and L. What is L? L is here. Minus mu times g times L can be taken from the first part, v0 squared over 2 mu g. So mu g is cancelled, v0 squared over 2, but with a minus sign. Therefore v, let me write it here, v squared is v0 squared minus 1 over 2. V0 squared minus v0 squared over 2. So v is equal to v0 over root 2. Now let's have another example where the force is not parallel to the surface but making a certain angle. Mass m is placed on an inclined plane. Where the coefficient of friction is mu, and the angle is theta. A force F brings the block or moves the block to a new position at a distance L from the first. During this process, find A, the work done by the force F. The work done by the force F, which is W sub capital F. The work done by the friction little f, so that it is W sub little f. The work done by gravity, which is W sub g. And maybe we can find the work done by the normal force, normal n, which is W sub n. And maybe we can find also the final velocity. The final velocity after having covered the distance L. So these are the parts of this problem. We will just use the definitions of the work, also the work energy principle. Part A, the work done by the force F. So let me draw the free body diagram first. Here is the object along the inclined plane. First we should draw the forces acting on it. Of course this is the weight mg. And this mg has two components. We know that mg cosine theta, because this angle is theta. Therefore this is mg sine theta. This is like a rectangle. And there's a normal force. There is the capital F. But this capital F, unlike the previous example, is not parallel to the surface. It has two components. One, let me draw that those components by black. So F has one component here, the other there. Let me write it as Fy and Fx. But this angle is also theta, so this is F cos theta, and that is F sine theta. Remember that this is also angle theta, and F is this one, so F sine theta is the opposite side, F cos theta is the adjacent side. And also we have the friction acting backward. Are you sure that it is acting backward? Yes, because otherwise this F wouldn't move it to the other part, so that assuming friction is acting in the downward sense. So work done by friction, work done by applied force F is just that force times distance times cosine, etc. But it is maybe easier to see this in this way. F has two components. One is parallel to the surface, and this is the direction of the displacement, because displacement takes place parallel to the plane. So this is the displacement of x. That component of F, which is in the same sense, is just F cos theta. So work done by friction is just F cos theta times this displacement L. So L is already given. WF is just F cos theta times L, or FL cos theta. Because F sine theta doesn't do any work. F sine theta component is perpendicular to the displacement. So they make an angle of 90 degrees, therefore there is no work done by this perpendicular component. F sine theta doesn't do any work. But it affects the normal force, and then therefore it affects the friction. Work done by friction is influenced by this perpendicular component of your applied force. But work done by capital L is just this much. Part B. Work done by friction. But what is friction? First of all, friction is mu times m. Friction takes its maximum value, first of all. Friction takes its maximum value. We are sure about it because the object is moving. Otherwise it will not move. F max, which is equal to mu times m. But what is m? Perpendicularly, F normal force n is just the sum of these two terms, mg cos theta and F sine theta. So that n is the sum of these two forces, F sine theta plus mg cosine theta. So that F can be written as, friction force can be written as mu times these two, F sine theta plus mg cos theta. Next, W, work done by friction force, it is this force, mu times capital F sine theta plus mg cosine theta, so that this part is just the friction force, multiplied by the distance L. But if you leave it as a positive term, it would mean friction is doing some positive work, it is just helping it. However, it is not helping us to move the object up the plane, it is just trying to prevent us from doing so. So there should be a minus sign. Why minus sign? Because as you see, friction force is acting down the plane, but displacement L is up the plane. So this angle is 180 degrees, and cosine 180, we have learned, is minus 1. So we have a negative term here. W little f is negative mu times this sum times this. All quantities are given by the problem. Next part is find the work done by gravity. Work done by gravity is just the force mg times this L times this vertical line. We have seen what the gravity does in such cases, in such lifting processes along an inclined plane. It is the gravity where mg, weight of the object, times this height with a minus sign. Minus sign comes from the directions. Mg times L, not L, but L times sine theta. Mg times L sine theta with a minus sign. Because although the object is going up, gravity is acting down. So this is the work done by gravity. Part D, work done by normal force. What can it be? This is the plane. The object is here. The object is moving along the distance L. But during all the motion, normal force is acting perpendicularly. When it comes here, perpendicular. When it comes there, perpendicular. So it is always acting perpendicularly. And acts on M perpendicular in the perpendicular direction, perpendicular to the surface, so that work done by normal force is just normal force times this displacement times cosine 90, and we know that cosine 90 is 0, so work done by normal force in such cases is just a 0. Just like the tension in a rope. When we come to those topics, tension, when you take an object and attach it to the end of a rope, for instance, and if you whirl it, rotate the object at the end of the rope, then tension in the rope doesn't do any work. because of the angle 90. Cosine 90 is 0. Now we have seen previously the mass spring systems. The mass spring system was the following. Let's remember that. We had a spring and a block attached to it at one end. The other end was fixed. When you assume this is the unstretched position, equilibrium position, when you try to elongate this spring to a greater position by a distance x, then we have to pull it, apply a force. We should apply a force F to this. But at the same time, the spring tries to take it back with some restoring force, Fr. So work done by this force can be found, and it is also important in several processes. Work done by the force in a mass spring system from the initial position of 0 to a final position where it is stretched by F, or by compression, doesn't matter, it is the same thing. Or if you want to compress it, by this distance x, and again you should apply a force F, but in the opposite sense there is a restoring force that tries to take the block to the unstretched position. In either case, we do some work in doing these operations, in stretching it or compressing it. What is the work done in this process? In this case, first of all, let me say that WF is not just F times x. Why? Because this F is not a constant force. So far we have seen these works done by some forces, but those forces were constant forces. So far F was constant. Constant means its magnitude doesn't change during this pulling or pushing process. This F in changing the position of the object was the same always. However, here F is not a constant. But now F is not a constant, instead it is a variable. What is F? F is k times, of course there's also a minus sign, but forget about this direction. Let me consider just the magnitude. F is just k times x. So it means the greater the value of x, the greater will be your force, or should be your force. Therefore, it is not just a simple multiplication. Instead, we should use an integration. So, a simple multiplication is not correct. Because if you just multiply, for instance, work done k times x is the force, multiply x by x, it will be just kx squared. However, this is not wrong as we will see. W is equal to kx squared is not correct. It is, there is one more term. How do you find the real correct value? By integrals. Therefore, we should use integration. What is that integration? W sub f is just an integral f dot dx. In physics, 101, you are not responsible for integrations, but this is how you get the correct value. It's an integral from initial value x is equal to, let's say, 0 to the final value of x. What is that f? It is k times x. So work done by force is integral k times x multiplied by dx multiplied by cosine 0. Remember that, it's a dot product, and f and x are in the same sense, so there's no angle between them. Cosine 0, yeah, cosine 0 is 1, alright. It is 1. But we have kx dx, and we know that if we have a term x to the n dx in an integral, we write it as x to the n plus 1 over n plus 1. And shouldn't be minus 1, by the way. 1 over x is different, and it doesn't belong to this group, but otherwise, if you have a power of x, such as 1 here, x to 1, it will be double, and plus 1 is 2, divided by 2. So work done by your force is just, k is a constant, we can take it out, k times x squared over 2, between 0 and the other value of x. So that WF, which you may remember from previous courses, is just 1/2 times k times x squared. So instead of just a kx squared, we have 1/2 times kx squared. So this is the main difference. So that just a simple multiplication is not correct. Now let's consider the concept of potential energy. In order to have a potential energy, we should have a conservative force. In order to talk about a potential energy, we should have conservative forces. Because some forces are conservative, some are non-conservative. We should have conservative forces, such as gravity, or spring force, Hooke's law. Conservative forces such as gravity or spring force. How do we differentiate these two types? If the work done by a force does not depend on the path taken, but only on the initial and final points. That is a conservative force. And gravity and spring force are two of such forces. In electricity also we will have work done by some forces, but in mechanics we have these two types. However, non-conservative forces such as friction depend, for those forces it depends also on the path taken. For instance, let's consider just a simple case, and also work done by this force F, let's say A to B to A is 0. What does it mean? From initial point A, by this force F, if the object goes to a new position B and then turns back to the initial point A, B, and then back to a initial point, the total work done should be 0. If it is so, we have a conservative force, such as gravity. For instance, if you throw an object, a ball, upward, it goes to a highest position, let's say initial position A, to a highest position B, and then turns back to A again. During this motion, total motion, work done from A to B, back to A is, what is it? In the first part, the object is here. Gravity is acting backward, but displacement is, let's call it y. It is negative mgy, because angle is 180. Negative m times g times y in the first half, but in the second half, both mg and y are in the same sense, so there is no angle. Here we have angle equals 0, here we have angle equals 180. Because of 180, we have a minus sign in the first half. Because of cosine 0, we have plus mgy, and they cancel, so we get 0, therefore it is a conservative force. However, friction, for instance, is not conservative, but let's consider a room, for instance. This is the top view of a room, corner A, corner B, corner C, and we want to bring a block. This is the top view of a rectangular room. We want to move it maybe directly along the diagonal, maybe first along this side and then along that side. So we arrive at a new position C by two different paths. There may be several different possibilities, but let's compare only these two cases. Now let us consider this object moved from point A, corner A to corner C in the room. This is the top view, by the way. This is the top view of a room. Let's say the length is A and width is B. So let's compare the two works done by friction. Work done by friction when it follows the path AC directly. In that case, work done is the friction force times the distance. What is the distance? It is just from Pythagorean theorem, root a squared plus b squared. And friction force is, using the horizontal picture, this is the surface, here is the block, and that's the weight mg, that is the normal force, and therefore friction is acting. If you move the object to this side from corner A to corner C, then friction is making an angle of 180 degrees with the horizontal, so that with the direction of the motion, so we have a cosine 180, which is minus 1. So we have friction forces mu times, mu is the coefficient, and that is mg, so that work done by friction along the path AC is negative coefficient of friction, weight of the object, and this distance a squared plus b squared. Let's keep it aside. On the other hand, if you follow the other path, first from A to B, then from B to C, work done by friction A to B to C in an L-shaped way, then friction force times this distance. That distance is just A plus B. Not the square root of that, but A plus B. So that work done by friction ABC, if you follow the other path, will be negative mu mg, but the rest is different. It is not root of this, but A plus B. So we understand that they are different. So these two are different. Work done by friction along AC is not the same as work done by friction along a different path ABC, although the initial and final points are the same. If you change the path, friction force does a different work. However, gravity, as we have seen here, does the same work irrespective of the motion. For example, if it does such a parabolic motion, if you do not throw the ball directly upward, but at a different angle, like a projectile motion, for instance, a goalkeeper sends the ball at a certain initial angle, it's a trajectory, parabolic trajectory, and then even in such throws, work done by gravity between the initial and final points will be 0. So it doesn't depend on the path. However, for the friction it does. So the friction is therefore, then friction is a non-conservative force. So that we cannot talk about the potential energy for a non-conservative force such as friction. The potential energy is defined, can be defined only for conservative forces. So what is the idea of potential energy? We can consider a single process, but in two ways. For example, when you leave a ball from a certain height, initial position, let's say initial position 1, it of course drops to ground, to the final position 2. Or first it is on the ground, it is thrown upward, and the first one is initial position is ground. It goes to a maximum height, it reaches the point 2, and then it comes back, of course. But one or the other. In these cases, we have found work done by gravity. And this work done by gravity can be equated to the change in the kinetic energy of the object. Maybe at the beginning it has 0 speed, but as it falls down, it gains speed, therefore it gains kinetic energy, and it hits the ground with a certain final kinetic energy of, let's say, 1/2 m times v squared, as we have learned. Or here for instance, initially it has an initial speed v0, so initial kinetic energy 1/2 m times v0 squared, and it goes up and reaches here where the velocity is just 0. For a moment it stops there and then turns back. So the kinetic energy final is also 0. In this process, from 1 to 2, if it goes upward, then work done by gravity, which is a negative quantity, minus mgy, if y is the total height here, mgy, this corresponds to change in the kinetic energy, minus 1/2 m times v0 squared. Or here, in the opposite process, initially it has 0 speed, but it is at a certain initial height. In this process, from 1 to 2, downward, work done by gravity is a positive process. Because work is force times distance, but dot product. Gravity is acting down, distance is also acting down, angle is 0. Work done by gravity is m times g times y. This is equal to 1/2 m v0 squared. Either both are positive or both are negative, so they cancel. However, the process tells us that if you look at the situation through the work point of view, the work done by force, here it is the only force is the gravity, weight of the object. If you analyze the situation through the work point of view, then work done by this force acting on the object creates a change in the kinetic energy. This is one way of looking at it. The other way is to define a quantity called potential energy. But potential energies are definable, can be considered only for conservative forces such as gravity or spring force. Now potential energy, for gravity is just, let me show it by capital U, it is mass times g times a certain height. But potential, when defining potential, which y can we take into account? For example, if we have a building here with several floors, stages. For example, assume that here we have a table. At the second floor, we have a table and a book on top of it. And this height is, let's say, for instance, 1 meter the height of the table is 1 meter, but this is, let's say, 3 and 3 meters. So totally this height may be, let's say, 6 meters. Also from the top of the building, this can be written as 9 meters. Which of these distances do we take as our y? For example, here is a table, and here is a book on top of it. But we are in second floor, for example. And the definition of potential is mgy. But which y should be taken into account correctly? Is it 1 meter, the height of the table? Or is it 6 meters from the ground? Or is it 9 meters, negative, minus 9 meters from the top of the building? Both can be taken. All can be taken. Not only 2, but all. Or any other height can also be defined as your y. For example, you can define the height of the book from the first floor, and it is just 3 plus 1, maybe 4 meters. This is also possible. How come can we have different values of y as valid numbers? Because this is not important. When you choose your y, when you choose your reference of y is not important. Anyway, this potential energy doesn't have a physical meaning. It can be considered different zeros, different reference positions, so it can have different potential energy values. But this is not physically important. What is important is the rest, because we can, let me write it first, we can choose different reference levels. Reference levels means y is equal to 0. You can set your 0 level anywhere you like. Okay? You can even choose very high positions if y is equal to 0, so that it is maybe minus 27 meters. All are possible. Because the problem doesn't end here, it continues. In general, problems tell us the subsequent motions, or we want to find the velocity of the object at a later position. For example, this book doesn't stay here indefinitely. It may be falling from the table. If it falls from the table and it hits the ground by some velocity, so here is the table, here is the object. Let's say it's a ball. The ball here has a certain potential energy, m times g times y. Y is up to us. And for example, it is just falling down and hitting the ground with some V final. What is the V final if it falls from a height y? In such cases, we choose the easiest one. For simplicity, we generally choose this level, nearest position, to be 0 level. Otherwise, of course, we could have chosen the ground level. The garden can be taken as your 0, so that this object has a certain initial potential energy. But in the first position, when the ball is here or the ball hits the ground, 1 and 2, initial and final, the energy is conserved. What is the energy that is conserved? It is the mechanical energy. Because we have seen that W, work done, corresponds to certain change in mechanics. But this W can be considered as the change in potential energy. So that total energy is also called mechanical energy. E is conserved. How do we get this idea? Very simply, it can be shown by different ways, but the simplest way may be delta U is delta K, but it is negative. Therefore, for instance, U2 minus U1 is equal to K1 minus K2. So if you take 1s to one side, 2s to the other side, U1, for instance here, U1 plus K1 is equal to U2 plus K2. But E is, the letter capital E is total mechanical energy. So this is first sum E1, this is the second sum E2. So E, which is the sum of the potential and kinetic energy terms is conserved. Conserved means its value doesn't change during the motion. So let's consider a very simple case. For instance, let's just apply it to a very simple situation as an example. For example, let's say this is the object of mass m. Initially, it is moving with an initial speed v0. Let's say the angle is also given on a frictionless surface. Okay. A block of mass m initially moving at velocity v0 starts to slide up a frictionless inclined plane of angle theta. Let's say part A. Up to which height y or h, up to which I little h, can it climb? B, what is its velocity? V at the height y is equal to h over 2 being going up and coming down. So let's very simply solve this easiest case. At the beginning, it has a speed, therefore it has an initial kinetic energy. You can choose any level you like as your zero level. For simplicity, we can choose this level as our y equals 0 level, and it reaches a certain maximum height. This height from the ground is h, and h is unknown. Since there is no friction, we only have a conservative force, which is the gravity. Of course, normal force doesn't do any work, we have seen it. We don't push it so that we don't apply any force, and there's no Wf, there's only Wg. But in this case, it doesn't say what is the work done by gravity, it says until which height, up to which height it can climb. So part A is simply let me give names to the positions, position 1 and position 2, initial and final. So total energy, mechanical energy E1 is the same as mechanical energy E2, or at any other intermediate position. E1, so what is E1? It is the sum of the kinetic and potential energy terms. At the beginning, it is the sum of the kinetic and potential energy terms at the end, or anywhere in between. If you choose this level to be 0 level, as we did, we have no potential energy. U1 is 0. What is the kinetic energy at the beginning? It has 1/2 mass and velocity 0, v0 squared. But what happens at the end? It has a certain height measured from the 0 level, the 0 reference, So it has mass times g times this unknown h. But since it stops here, it stops for a moment and then comes back. So that b is 0. Therefore, there is no kinetic energy. If you neglect these zeros and cancel then the masses, h will be v0 squared over 2g. H will be v0 squared over 2g. So this is the result to the height it can reach. The greater the velocity, of course, the greater will be the height. Part B, what is its velocity v at the height? Half of it. So that, let me consider this intermediate position as the point 3. So this height from the ground is just, let's say, h over 2 for instance. This time E1 is equal to E3. Of course, E1, E2, E3 total value of the energies is always the same during all the motion. E1 at the beginning is also equal to E3, and it doesn't depend on going up or coming down. In going up and coming down, there's no difference. Why is there no difference? Because it's a frictionless plane. If there were some friction, of course, going up and coming down parts would correspond to different velocities, as we will solve next. So E1 and E3 are equal. What is E1? U1 plus K1. The other one is U3 plus K3. U1 is, at the beginning, we have chosen it to be 0. K1 is 1/2 mass of the object, initial velocity squared. U3, now it corresponds to such a height, m times g times h over 2, plus, now there is some velocity, of course, there is some kinetic energy, 1/2 m times v, let me call it v3 squared. So we can cancel the masses. You can also cancel these 2's, and we have v0 squared on the left. G times h. What was h? We already calculated h to be this quantity, v0 squared over 2g. Now plus v3 squared. So these g's will cancel. v0 squared minus v0 squared over 2 corresponds to v3 squared. So 1/2. Therefore v3 corresponds to v0 over root 2. Comment. Since there is no friction, V3 is the same in going up and coming down. But if there were some friction, the block would have a smaller velocity in coming down with respect to going up, because during the whole motion friction force will do negative work on the object so that it reaches point 3 in going up with a certain velocity. Let me give numbers, for instance. If it were such a value, for example, 10 meters per second here, it will be, let's say, 8 into 0, for example. Not 10 and 8, of course, but let's consider this value. If it were, for example, 10 meters per second, in going up it would 10 over root 2. Now, 10 over root 2. Root 2. When it comes to the total height h, it reaches the 0 speed. And then coming up, coming down, again it would have the same speed, 10 over root 2. And it reaches the lowest position with this initial speed, 10 meters per second. However, if there were friction, this velocity, now let me draw a schematic picture now. Let's say this is V0 at the beginning. Reaches here some V3. Here it reaches V2. V2 is 0. And when it is coming down, this speed V3 prime would be less than V3, whose value was the speed corresponding to the halfway point in going up.